Today we have with us Dr. Bruce Mac, who got his PhD at UCLA in 1994, working on infrared instrumentation and brown dwarfs. He was a postdoc at Lawrence Livermore's Institute for Geophysics and Planetary Physics, working for Claire Max and Scott Olivier, and then a physicist in the adaptive optics group and various divisions that merged and evolved into the physics division. He co-group discovered the H8799 planetary system in 2008 and won the AAAS Newcomb Cleveland Prize for that work. Bruce was the principal investigator for the Gemini Planet Imager program, and in 2014 he left Lawrence Livermore for Stanford, where he is now a professor in the physics department and deputy director of the Kavli Institute for Particle Astrophysics and Cosmology. And it was suggested to me that I share this picture from time long ago. But for nostalgia, this is back when Bruce Mac optics program. People have changes with. I hear there's been some conservation of hair principle involved. Anyway, great to learn about some of the past work that Bruce did here at Livermore, and it's good to have him here. Let me remind everybody that this meeting is being recorded, so if you're not comfortable with that, please log off. Also, videos have been put online and are available now on the Lawrence YouTube channel. And this is an unclassified meeting, and please be aware of that in the comments, and there are people logged in from outside the lab. Otherwise, I like to pass things over to Bruce, and I look forward to this talk. Thank you for joining us. Bruce, are you able to share your?
There we go. Okay, pardon me, I was muted. I was just gonna, before I started showing my slides, thank you for the introduction and for the invitation, and sort of looking at the list and seeing a few familiar names in the audience, and regretting that I can't be there in person. I was sort of telling Paul before I started that there's a lot I miss about my time at Lawrence Livermore Labs. It was an extraordinary experience that taught me a lot. That I try to keep with me now that I'm in an academic environment. And I was maybe almost even feeling nostalgic for the beryllium safety training, although that might be going a little too far. And for some weird coincidental reason, I got an email from Livermore Information Management last week asking me to put papers that I did 8 years ago in for review and release. And so if anyone wants to volunteer to help me with that, that would be great. But yeah, it's great to be talking to everybody. And I'm going to be presenting work. Is my screen share working properly for the PowerPoint?
Yes.
That is really the culmination of work by an extraordinarily large and highly talented team who I don't have time to credit really anywhere near everyone of. But again, I'd highlight especially the people I worked with at LNL. A series of outstanding postdoctoral researchers, some of whom have remained at the lab, some of whom have moved on, who did a huge amount of science with me, sort of just supervising and signing the checks, and the Lawrence Livermore Adaptive Optics Group, who are really responsible for the construction of the Gemini Planet Imager instrument that is responsible for a lot of the results here. Let's talk about what I'm talking about. And for this audience, I'm going to try to focus a little more on the science side rather than the optics and technology. There's a whole other talk I could do about the adaptive optic system and how we control diffraction and how we measure wavefronts at nanometer accuracy, and I would love to do that. There's a whole other talk, which I think I alluded to in my abstract, but cut for time, about concepts we have for small sats for doing exoplanet detection and characterization. Instead, I'm going to concentrate on the study of planets through direct imaging. And what that means is actually seeing a planet. It turns out most of the time when astronomers have discovered the 4,000 known extrasolar planets, they don't see the planet, they see its effects on the parent star a Doppler shift caused by its gravity, or the parent star getting fainter as the planet blocks some of its light. What we do, and this traces back to work that people like Scott Olivier began at Livermore long ago, is try to actually see the planet, to block out the star and see a tiny planetary signal only a microradian away from it. It's challenging. It has complicated selection effects, but it's a unique way to probe especially big Jupiter-like planets. So I'll talk a little bit about why we want to do that. I'll review a little about planet formation and what imaging tells us. I'll talk a lot about the HRD 799 system, the 4-planet system that we discovered 10 years ago. And then I'll talk about uncertainties in our modeling and understanding of it. There's challenges in getting models that reproduce the spectra of the planets we see, which might provide clues to interesting physics that's happening in them. Then I'll talk about GPI, the Gemini Planet Imager, the next instrument we put together to push sensitivity beyond it. And if there's time, I'll talk about the future, the upgrades we're planning for GPI into something we call GPI 2. I alluded to this a little bit, just that direct imaging is a nice way to study the outer parts of solar systems. The other techniques astronomers use really study stuff that orbit inside the orbit of Venus or inside the orbit of Mercury, really. Most of those 4,000 planets we know would orbit closer to the sun than Mercury does if they were in our solar system. Imaging, is on the other hand, is a way to study the outer parts where in our solar system the giant planets live. Those giant planets are important because they're a record of the formation of the planetary system. Jupiter, which represents by far the majority of the mass among planets, traces and retains information in its composition about how planets formed. And in turn, understanding whether planet formation in our solar system, we know that planet formation process, though, produced not just Jupiter, but an Earth that we can stand here and live on with a nice thin atmosphere, just the right amount of water, etc. We don't know if the process that formed planets in other solar systems can do that or not. Part of how we'll answer that is by studying the smaller planets in those solar systems. Part of how we'll answer that is by understanding the process through which planets form and evolve. And ultimately, if we do want to study true Earth analogs, planets the size of the Earth orbiting one astronomical unit from their star, that's going to be done through direct imaging. Not now, we have nowhere near the technology needed to do it. It's going to take future space missions that include things like adaptive optics and diffraction control. But with those, it's possible to imagine a version of me or my students 20 years from now giving this talk, except instead of showing spectra of Jupiters, they're going to show spectra of Earth. And instead of talking about why there's no methane, they're going to talk about why there's no oxygen, or why there is oxygen. And then again, for a mixed audience, I tend to lapse into astronomer speak. So this is the glossary. I should have handed it out electronically beforehand. I'll talk a lot about the luminosity of planets. In our terms, that's just the total power radiated by a star or a galaxy or a planet or a space potato or whatever. Because it's power, the units for it are watts. But watts are kind of an unnatural unit. I mean, if I could see you, I'd ask you to raise your hands if you knew the luminosity of the sun in watts, because you probably don't, and I would not raise my hand. So the natural units tend to be solar luminosities compared to the luminosity of the sun. We'll also show some graphs of flux. In astronomer terminology, flux is what other people might call a radiance, power per square meter. I'll talk about metals, and when astronomers say metals, we don't mean metals. We mean everything that's not hydrogen or helium. It's just a weird convention our field is stuck with. So for me, oxygen, metal. Metallicity, the fraction of an object that's not hydrogen or helium. Contrast, when we're looking for planets, the ratio of brightness between a planet and a star. And then units, we'll often use the astronomical unit as a distance unit, distance between the sun and the Earth. So take screenshots of this so that you can get the terminology right. And reminding you of context, just a picture of our solar system, the 2021 version of it. So there's only 8 planets, not 9. In our solar system, there's this very natural break between rocky planets in the inner solar system and giant planets in the outer solar system. And if I plot that as a graph, I'll show a couple of times scatter plots like this that compare the mass of planets in Earth masses, in this case, versus their orbital radius in astronomical units as kind of a natural unit counterpart. This is what the figure looked like in 1988. It's also what the figure looked like when I came to Lawrence Livermore in 1994. There were basically 8 or 9 planets known, depending on how you count, and they broke clearly into this group of large, giant gaseous planets with low densities, with compositions that are dominated by hydrogen and helium, and small rocky planets like the one that we're standing on in the inner solar system. And when I went to graduate school, I was taught pretty much every solar system would look like this. In hindsight, that's extraordinarily embarrassing, almost pre-Copernican, but that was the view we had, that the process that formed our solar system had to be the only natural process to form any solar systems. What was that process? Well, it started with a large cloud of interstellar gas that contracts, and as it contracts, heats and flattens. It heats because gravitational potential energy is getting converted into thermal energy, and it flattens from conservation of angular momentum as it goes from rotating very slowly to rotating very quickly. In turn, that disk then develops a temperature gradient. At the center is kind of a protostar. Further out, close to the center of the disk, it's hot. Further out, it's cold. The disk is mostly hydrogen and helium, but embedded in it are other materials, the metals, air quotes, iron, carbon, oxygen, and so on. In the big interstellar cloud, those are all in the form of little solid grains of carbon and oxygen, water ice, iron, and silicates. In the disk, when you get close to the star, those grains vaporize. Far from the star, they survive. And so early on, there's a segregation between rocky material close to the star and icy material further out. And this kind of cartoon, there's dots indicating tiny little dust grains of rocky material and tiny little dust grains of icy material. As the disk rotates, those grains stick together and form bigger and bigger lumps that can start to turn into planets. They go from micron-sized grains to millimeter-sized grains to centimeter to meter to kilometer-sized gray objects that we call planetesimals. And then they keep colliding larger and larger and larger to form protoplanets, protoplanetary cores. And that process happens much faster in this model in the outer parts of the disk because there's much more material there to build cores out of. There's ice. In the inner parts of the disk, the only stuff that's solid is iron and silicon and silicates, and iron and silicates are pretty rare in the universe. So the planet-forming seeds build much more quickly in the outer parts of disk. When they get big enough, they actually start to clear a gap in their neighborhood from gravitational torques and orbital interactions, and slowly keep growing. When they get even bigger, eventually, when these cores are maybe 10 times the mass of the Earth, they're big enough to start to schloop gas from the disk itself, suck up an atmosphere, and turn into something like Jupiter. In that model, the only way you'd get something like Jupiter then is in an outer part of a solar system where there's lots of planet-building material. When you did it, it would be an icy core surrounded by a huge hydrogen atmosphere envelope. Every solar system would look like our own. And of course, now that we know thousands of extrasolar planets, none of them look like our own. This is a scatter plot, 2 years old, so it's missing about 1,000 planets, color-coded by discovery technique of most of the known extrasolar planets. And they're not like ours at all. There's this huge population of planets that are the mass of Jupiter, but orbit closer to their sun than Mercury does. We call them, unimaginatively, hot Jupiters. There's a large population of planets that are kind of like Jupiter, but still tend to be closer to their sun, sort of semi-classical giant planets. There's a population discovered through our technique of giant planets on wide orbits that are much more massive than Jupiter and much wider orbits. There's objects we call brown dwarfs. I won't talk about that much. There's objects that are the size of Neptune or smaller, mini Neptunes, but again, orbit extremely close to their sun. And then there's planets that are bigger than Earth that if you're an optimist, you call super Earths because you like to imagine that they have atmospheres and life and things like that on them. And we recognize that this is not by any means a complete sample, however, that you can see that the detection techniques we're using are biased, that there's kind of selection effects along here. And so it's not necessarily that solar systems and planets like our own don't exist, it's that our techniques aren't sensitive to them. And the main techniques for studying extrasolar planets these days, transits, are clearly very biased to this inner solar system sample. They're powerful, but the sample they're giving us is not at all representative, we think. So if we have planets like Jupiter, but way too close to the star, how did they get there? There's a bunch of models to form these weird solar systems. One just involves migration. You might produce a planet like Jupiter the old-fashioned way, and then it just moves into its star while it's still forming. when you've got a planet embedded in a disk, it experiences a gravitational torque that's almost like friction that can pull it in closer to the star. And then when the disk goes away, you have a Jupiter close to the star. You probably don't have an Earth close to the star because the Jupiter will throw it out of the solar system or dump it into the sun. In which case, if that's how most solar systems form, that's kind of bad news for Earth analogs. It probably isn't, as a spoiler. Alternatively, this slow process where you form a planet by sucking up gas from the protoplanetary disk, by forming a core first and then sucking up gas, might not be the main pathway to planet formation. These disks can be unstable. The numerical simulation of a large disk, you can see it orbiting around, and you can see it starting to develop structure from self-gravity combined with a relatively cold temperature. The disk begins to develop spirals and then fragment into distinct protoplanetary lumps that will turn into planets. In this model, multiple planets. That process is actually really rapid and honestly kind of unphysically rapid in simulations like this. If you watch the simulation, it took about 6 or 7 or 8 orbits to form the planet, which represents maybe 600 years. The disk is supposed to be 1 million years old. And so basically the disk sits there for 1 million years, and the moment you turn on your computer simulation, it falls apart completely into planets. A colleague of mine likened this to simulating having a pencil balanced on its end and using thousands of hours of computer time to simulate the fact that it falls over, as opposed to asking the question, how did the pencil get balanced on its end in the first place? So these simulations don't necessarily represent plausible initial conditions, but they do show that large instabilities can be important. And so in that, your disk just rapidly turns into a bunch of planets. So how might we understand which of these processes are going through? We've gone through. One way is to study the chemistry of the planets. The gas and the gas disk, and then the solid seeds that form the core of the planet have very different carbon to oxygen to hydrogen ratios. In the inner parts of the disk where it's really hot, the carbon to oxygen to hydrogen ratios are basically interstellar gas ratios. Further away, where it's cold enough for solid material to form, past what we call the frost line, a lot of the oxygen gets locked up in water ice grains, and so the carbon to oxygen ratio goes up. Further out, even more oxygen gets locked up in CO2 grains, and the carbon to oxygen ratio goes up even more. And then way, way, way out, it looks like interstellar gas again. And if you form a planet, it'll be a mixture of the solid material in a core, gaseous material, and then maybe additional solid material that got dissolved in its atmosphere. And the presence of those different elements tells you something about how it formed. And in fact, in the case of Jupiter, our biggest clue that Jupiter formed in a way that involved assembling solid material comes from things like its elemental abundances. These are reasonably up-to-date values of the ratio of abundance for Jupiter to the sun. Helium is basically sun-like. Neon I'm not going to talk about. Most other elements are enhanced by about a factor of 3. The only way we can think of to do that is that it accreted material in the form of solids, whether to form its core or its interior. Does that happen for other planets? Well, the people using transit techniques, so transits, I apologize for not explaining, refers to when a planet basically passes in front of its star and blocks a little bit of the light from the star. Planets are opaque. And so when you do that, the star gets about 1% fainter. Tiny, but fairly easy to measure with modern equipment, even small telescopes. Transits, as I said, are most powerful close to the star, so they've been a good way to study the hot Jupiter planets and these many Neptunes. And you can even use transits to study spectroscopy. At the moment the planet is passing in front of the star, most of the light from the star gets blocked, but some lines of sight from the star graze the planet's atmosphere and just barely reach the Earth, in which case you'll see the absorption signature of the chemical composition of that atmosphere. That's been done for a fair number of planets, mostly with space telescopes. This is kind of a representative pseudo-spectrum. It's not exactly a spectrum, but it's spectrum-like, basically how much light gets absorbed, and showing clear features associated with things like water vapor and carbon monoxide and methane. In the case of this planet, that fit to explain all those absorption features actually does require a huge amount of heavy elements mixed into the planet's atmosphere, even more than we see in Neptune and Jupiter. And people have made plots of the heavy element fraction, what I call the metallicity, relative to the sun, versus planet's mass. in our solar system, there's a trend. The smaller planets tend to have more heavy elements in them because they're mostly made of solid material. The lighter planets have less heavy elements in them. The extrasolar planets kind of reproduce that trend, but you shouldn't really believe the error bars on any of these. And you should remember that this sample studied with transit techniques is the planets that are right next to their sun, which may in turn have influenced their evolution. They may have lost their hydrogen because the planet they heated up. So you can't really, this says, oh, WASP-12b, it looks kind of like Jupiter, but WASP-12b is hotter than Mercury. And so the fact that its heavy element fraction looks like Jupiter's might just be a coincidence, not indicating anything fundamental. So these different planet formation pathways, the core accretion process, form the core first, maybe migrate the planet. The global instabilities of planets make different predictions about what their properties are going to be. And studying those different predictions is what we're trying to do with direct imaging and with a variety of other techniques. All right, so when I talk to my students, since we're all doing Zoom classes, I usually like to give them a break periodically and show them pictures of our family's golden retrievers. So you now get a dog break for about a minute, and I'm willing to take questions, although if Paul would prefer that we save questions for later, that's also good too. But it feels like as I go from theory to observations, this was a good time to stare at a picture of a puppy. Okay. I can't see the chat window, by the way WebEx is organized. So if people are trying to interrupt me in the chat window, there's very little hope that I'll see it. So on to imaging, the stuff that our group actually does. So the imaging planets are these ones living up here in the upper right, kind of wide orbit planets. And again, you can see it's a pretty biased sample. We're not seeing planets like Jupiter, let alone Venus and Earth or Uranus and Neptune. We're seeing planets farther from the star and that are more massive. And so why is that? Mostly it's because it's really hard to see planets with direct imaging. This is a plot of contrast, the ratio of brightness between the planet and a sun-like star versus angular separation, how many seconds of arc the planet appears to be away from the star for our solar system. And you can see the brightest thing in our solar system, Jupiter, is 10 to the minus 9 times fainter than the sun. As seen from outside, it's a billion times fainter than the sun, and it's separated by 1 second of arc, 5 microradians, if you were to see our solar system from 15 light years away. And that's pretty hard to overcome, by which I mean impossible with current technology. You might say, all right, just point the Hubble Space Telescope at a star and see if we see any planets. So here's what happens if you point the Hubble Space Telescope at a star. These are images of a very bright star observed with the Hubble Space Telescope. The star is blocked out by a star blocking mask. And what you're seeing, well, this dot down here is actually an internal, I believe it's an internal optical ghost, not a planet. I wouldn't swear either way, not a star, excuse me, either way. But in either case, it's 10 to the 5th times brighter than Jupiter would be. If there was a Jupiter in this image, it would be 10 to the 5th times fainter than this thing, and it would be 10 times closer. And so it'd be completely lost in this sea of scattered light. The scattered light is mostly diffraction from the telescope geometry, from polishing errors on the telescope primary mirror, from the secondary spiders, a whole mess of things. But with all of its capabilities, Hubble can see things that are about 10 to the 4th to 10 to the 5th times fainter than the parent star. The sensitive range for Hubble is up here, long way from Jupiter. So if we were going to see planets with current technology, we need brighter planets. How could I get brighter planets? Well, one thing you might say is, all right, let's get some bigger planets. That might make life bigger, right? Jupiter's big, but maybe planets could be more massive than Jupiter. In fact, they can. Planets can be 10 times as massive as Jupiter or 20 or 30 times as massive as Jupiter. Would that help? Mostly no. The equation of state and the interior structure of these planets means that their radius is nearly independent of mass. This is a plot of planet radius versus planetary mass in Jupiter masses. So Jupiter would live right here. And basically all the way from Saturn masses or even below up to 10 or 30 times or 70 times Jupiter mass, the radius doesn't change much. For smaller planets, Coulomb repulsion and the details of their equation of state, metallic hydrogen, give you a mass radius that's nearly independent. For brown dwarfs, the radius actually starts to decrease with mass because the planets are partially degenerate in their interior, and degeneracy pressure produces that behavior. Coincidentally, these things basically line up with each other to give you everything as a Jupiter radius. It's extremely hard to make a planet that's smaller than a Jupiter radius, and it's very hard to make one that's bigger unless you heat it up somehow, which might help. So planets are giant planets, pretty much all the same size as far as we know. I'll talk about some limitations of that later. So instead, we might look for planets in a way that makes them brighter. So this actually just came out as a press release this week. It's a beautiful Hubble Space Telescope image in visible light of Jupiter. You can see the great red spot, you can see the clouds and different patterns. At the same time, they took an infrared image with the Gemini telescope at mid to near infrared wavelengths. And that's what Jupiter looks like at mid to near IR wavelengths. What you're seeing here is in between the clouds, you're seeing down into the warm interior of Jupiter. Jupiter is hot on the inside. And so at some locations, Jupiter glows, not because of sunlight, but because the interior is hot. And in fact, in Jupiter's case, that heat is left over from its formation. Jupiter radiates about twice as much energy as it gets from the sun, partially because it's still contracting, and so gravitational potential energy is being released, partially just because when we formed Jupiter, a hell of a lot of energy got put into its interior. So Jupiter is about twice as bright at infrared wavelengths as it is at visible wavelengths because of this glow. If we could find something like Jupiter when it was young, it might be 1,000 times brighter than this, or 100,000 times, because it will release a huge amount of energy and then spend the next billion years or so cooling off. This was predicted by people like Adam Burrows. This is a nice graph of luminosity, absolute brightness compared to the sun symbol, versus age from 1 million, 10 million, 100 million, billion, 10 billion years. Up at the top are stars. They go through some initial gravitational contraction, cool off, and then settle down, happily burning hydrogen and having a steady luminosity forever. At the bottom are planets. These are masses in solar masses, so this is a Jupiter-like planet. It basically initially might be only 10 to the minus 5 times as bright as the sun from that initial gravitational potential energy, and then just contract down. And then in between are objects we call brown dwarfs. They have kind of a bump because they're massive enough to fuse deuterium for a tiny fraction of their life. Deuterium, as you all know better than me, is really easy to fuse. And so after that deuterium burning phase is over, they run out of it in like 10 million years, and then they settle down and cool like the planets do. So if we could find stars that are, say, 10 million years old, their Jupiters would only be 10 to the minus 5th fainter than the sun. Still couldn't see them with Hubble, but if I had a bigger telescope, like say the two Keck telescopes and the adaptive optic system that Lawrence Livermore helped build for them, I could probably see them. So this is a sensitivity curve for the adaptive optic system on the Keck telescope, and the dots now are 30 million year old planets that are a little more massive than Jupiter, enormously brighter than Jupiter at infrared wavelengths. And so we set out to find objects like that, starting when I was at LNL, and in 2008 we had a beautiful success. We found a system called HRID 799 where we saw not one, not two. We thought there were two. Is someone speaking or is just someone unmuted? 3, but four planets orbiting around it. The star in the center. Oh,
Look at that graphing table again. Will it fit?
I'm guessing that's not intended for me, but I'll assume otherwise. I will carry on unless someone forces me to stop. There are 3 planets that have a temperature of about 1,000 Kelvin, a mass 5 to 7 times the mass of Jupiter. Outermost one, a little bit cooler, a little bit lower mass, 3 to 5 times the mass of Jupiter. It's an amazing system that would fill up an entire talk. There are a couple of things to note about it. Well, let me show. We've actually watched this system now for 10 years, which means not only can we see the planets, we can actually see them orbit. So this is about 7 years of real data animated by a former student, Jason Wang. and essentially real data. What you're seeing in the center, the star is blocked out, and all this is still residual diffracted starlight interference speckles. So that's not real, but these are real. This is the real near infrared brightness of the 4 planets. Over the course of 7 years, we can actually see them orbit. They're orbiting just like Kepler and Newton said they would, which is not a surprise, not like Kepler's laws are new, but the fact that we can actually see Kepler's laws from outside over the course of a chunk of one's professional career is just beyond amazing. And there's a whole separate set of talks about measuring their orbits and their gravitational interactions and what that tells us about their masses and so on. I could like just stare and watch at this all day, but I'm here to do a talk, so I won't. Characterizing them starts with looking at those luminosities at their total flux. So this is a busy plot, and I want you just for now just to look at the measurements. All of these data points are measurements of the planet's brightness at different wavelengths. The lines are model fits to the planet, which I'll return to later, and have huge amounts of uncertainty. There are gaps in our measurement because we're making them from the Earth, and the Earth's atmosphere absorbs certain wavelengths of light, like here. But as long as I'm willing to use a model to fill in those gaps, we actually do have measurements that pretty much span most of the flux coming from the planet. And so we can get a pretty good estimate of the planet's total luminosity, of its brightness relative to the sun. We also think we know the age, not of the planets, but of the star they're orbiting. And the planets obviously can't be younger than the star, older than the star. And so I can go to these cooling diagrams where I have a luminosity versus an age, and I can put the planets on them. This is where one of those planets in that system lives. Each line corresponds to a different mass in Jupiter masses, 1, 2, 3, 4, 5, 6, 7. And so from the fact that the luminosity is around 10 to the minus 5 solar and the age is around 30 million years, I can infer that the planet's about 7 Jupiter masses. So I actually know the masses of the planets, I would say, pretty well up to some modeling uncertainties. The next step in trying to understand them is to look at their spectra. So a little bit of astrophysics, some people will be familiar with, some people won't, but the spectra of stars is sort of toys of the atmosphere of a star or a planet. It's cooler on the top, it's hotter and denser on the bottom. In the case of a star, the interior is pretty opaque. It's atomic and molecular hydrogen and also H-, negatively ionized hydrogen, which is a really cool species, that are basically opaque. And so radiation comes up from the interior with a black body spectrum. As the radiation gets higher, though, it gets absorbed by species like water and carbon monoxide in the gas. And so you get a spectrum that's essentially a black body, but with absorption features from water, carbon monoxide, a little bit of atomic stuff. But stars kind of look like black bodies. Brown dwarfs or hot planets start to look less like that. At a temperature of 1500 Kelvin, stuff starts to solidify. Iron condenses into liquid metal, magnesium silicates, and you get an opaque layer pretty high up in the object's atmosphere at more like 1500 Kelvin temperatures. Radiation from that still goes through the atmosphere. The chemistry in the planet's atmosphere favors carbon monoxide more because it's cooler, and so you get spectra that are dominated by things like absorption from water vapor, absorption from carbon monoxide. They're black bodies still, but they're black bodies that have had now really big bites taken out of them. As you drop temperatures further down to, say, 1000 Kelvin, the structure gets even more complicated. The clouds are deeper in the planet's atmosphere where they're barely visible. On the way up, the radiation the chemistry now allows things like methane to form. And so the planet's spectra changes enormously with wavelength. At some wavelengths, you can see deep into the planet's interior and see those hot metallic iron clouds, and the planet's really bright. At other wavelengths, methane is an incredibly good absorber. You just see the cold top of the planet's atmosphere. And so the spectra start to look nothing like black bodies, with huge variations in brightness as a function of wavelength because of the presence of elements like methane. And that's what we thought we would see in the 8799 planets, but it's not what we saw. We actually saw a spectra that looks more like a brown dwarf than a planet, like a hotter object. We still see the water vapor feature. We still see carbon monoxide. We still see, but we don't see any of the methane that chemistry predicted should be present in the planet's atmosphere given its temperature. We spent a huge amount of time arguing about this. One thing people suggested was, well, just the planet's hotter than your models think it is. I'll talk about why that's not true in a little while. An alternative explanation is that the planet's atmosphere is circulating, that the clouds, the opaque layers of metal and silicates, are circulating up where they're more visible, and the methane is circulating down where it gets destroyed in the hot, deeper layers of the planet's atmosphere. It turns out methane is really hard to make. The chemical reaction network that leads to it is extremely slow, and so you don't need a lot of circulation to destroy the methane. So models can kind of maybe explain why we didn't see the chemistry we thought we would see. They still mess up, though. These models tend to produce quite high temperatures, as a result of which they produce quite small radii. The best fit models for the planet have radius that are about 3/4, the radius of Jupiter. And I'll talk in a slide or two about why we don't like that. We can get even better spectra. Actually, this is a high resolution spectra from work by Quinn Konopaki, showing individual carbon monoxide absorption lines. And that does let us start to probe things like the carbon to oxygen ratio, where the solar value of the ratio to carbon to oxygen is about 0.55. It does look like maybe there's some enhancement in carbon compared to oxygen, which is hints of the sort of chemistry that I was alluding to. But what keeps me up, it doesn't keep me up at nights a lot, but what worries me is the radii that come out of these models are usually wrong. Here was this mass radius graph I had. This is where the 8799 planets tend to come. And that's very hard to explain, and I'll talk in a little bit about explanations for why. I think I'm going to skip a discussion of initial. I'm just trying to think about how to balance my talk. I think I'm going to skip a little bit of discussions of initial condition sensitivity. It's something I could come back to if people are curious, except just to say that these models of these cooling planets, as they start with planets here, how did I get a planet to start cooling down? These modeled formation very adiabatically, as if the planet started as a cloud of gas that just wafted down into a planet very gently. Almost certainly that's not how you form a planet. And changing the initial conditions is another window we have into the planet formation process. And I'll come back to that if people are curious. But I wanted to talk about GPI a little because GPI is awesome. And it was the major thing in my last years at Lawrence Livermore. So the Gemini Planet Imager was built to go beyond what we could do with Keck and be maybe 10 times more sensitive to planets to see lower mass planets closer to their star. It was built by LNL. We were responsible for the adaptive optics system, by the American Museum of Natural History, who worked on diffraction control, a weird thing for a museum, long story. We put a lot of work into having super polished optics characterized with things like the metrology developed at Livermore. We have an infrared spectrograph that makes both images and spectra of planets, built by UCLA. The whole structure of the instrument was built by the National Research Council of Canada, as well as the software that connects all the pieces of instruments. I see a question from Lauren, but I think Paul was saying maybe we'll defer those to the end, if that's okay. A very sophisticated data pipeline, and then Livermore was the lead institution responsible for project management, in particular Dave Palmer. It goes on the Gemini South telescope in Chile, a beautiful telescope. There's the instrument bolted to the back of the telescope. It weighs about 2,000 kilograms. There's the team just after First Light, including Dave, including Lisa Poinier, including a large number of scientists from a whole bunch of other institutions. Here's a First Light image for GPI. For our First Light, we looked at planets we knew existed. So what you're seeing here is a star blocked by a mask and kind of glinting off the edge of it, and one of these planets. In this case, it's 10 to the 5th times fainter than the star. A pretty good detection. Especially compared to detections with previous instruments like the Gemini Niki instrument that is one of our predecessors, and doubly especially because this image with a previous generation instrument took an hour and the GPI image took 60 seconds. So GPI was significantly more sensitive than Keck, especially close to the star. Would we find planets? We looked at about 600 stars that are young and near the sun to try and characterize them. Again, an image of the large science team that did it. Initially, we did this by flying down to Chile, but even pre-pandemic, we kind of transitioned into remote controlling the instrument from the Northern Hemisphere. This is your second puppy break also, on an occasion observing from Stanford when I had to bring the dogs in to help us with remote observing. We're also helped by a sophisticated data processing architecture that takes complicated GPI data sets and turns them into planet detections that post on Slack in kind of quasi real time. Using GPI, we found a total of 6 planets and 4 brown dwarfs, many fewer than we thought we would find. And I'll talk a little bit about why. As we spent a lot of time characterizing them. We measured their spectra, ranging from the hottest objects that look more black-body-ish to the coldest object we found. That coldest object, 51 Eridani B, at the time was the coldest exoplanet discovered through direct imaging. It orbits still in the outer parts of solar system, but kind of Saturn-like. But its spectra finally showed these deep methane absorption that we expected to exist in the colder planets. And this is the data points with error bars are 51 Eridani B. The line here is the spectrum of Jupiter. If you'd shown this to an astrophysicist 80 years ago, they would have said, oh yeah, that's Jupiter. It looks like a planet, not like a brown dwarf. Models still don't fit it very well, though. This is a grid of models with different temperatures from 700 to 900 Kelvin, different gravities, which weakly affects the spectra, different metallicities, different cloud properties. Some of them do okay, but the best fits still tend to have radii that are around 0.7 times the radius of Jupiter, which we still think is implausible given the physical properties of the planets, especially because these younger planets should actually be bigger than this line because they're still puffed up from their initial heat of formation. What could explain that? Could the equation of state be wrong, which is what determines the interior structural? You would all know better than me, but I kind of think no. I'm inclined to trust the comparatively simple physics of the interior. Also, people have discovered with transit techniques older planets, and they're where they're supposed to be. They tend to be Jupiter size like they're supposed to be. The structure of the planet could be wrong. If the planet isn't mostly hydrogen and helium, but I put a big core of heavy elements in it, that will contract the planet down. A dense non-hydrogen core would make the planet substantially smaller. The problem is it would have to be huge. I would need 100 Earth masses of solid material in the core to make the planets that much smaller. It's challenging to do that in a formation model. The most likely suspect is just that the atmosphere models are wrong. The details of getting all of this chemistry and especially the cloud structure is very complicated. If the models are overestimating the temperature of the planet, if the models say the planet is 900 Kelvin and it's really 700 Kelvin, they will also overestimate the flux per unit area and cause you to underestimate the radius. And certainly the treatment of the clouds and the chemistry and the vertical circulation in these models is primitive. Our planets are spheres, spherical cows. You know, here's the infrared image of Jupiter. If I looked at Jupiter at infrared wavelengths and I just added up the brightness of it, I would only really be getting brightness from the fraction of this area where I'm seeing through gaps in the clouds. I'd get Jupiter's radius wrong. So one possibility is just real complicated three-dimensional structure in the planet's atmosphere. There could also be additional sources of opacity that are making the planets look smaller, wrong compared to what they should be. And an interesting possibility for that is that all of these young planets and young stars are surrounded by massive asteroid and comet belts because they're still in their early chaotic phases of their evolution, with maybe 100 times as many asteroids and comets as our solar system, or 1,000 times. And even in our solar system, comets and asteroids smack into things, not into the Earth very often, fortunately, but into Jupiter. This is the impact of comet Shoemaker-Levy 9 on Jupiter. The actual impact wasn't observed, but after the impact, it left these huge scars in Jupiter's atmosphere of extra dusty material that persisted for weeks. In our solar system, Jupiter probably gets hit by a comet like this every couple of years. In these young solar systems, the giant planets probably get hit by a comet every week. And so we're experimenting with adding kind of rains of dust into the planet models that simulate being smacked into by a comet every week. Early results from that by my student Alec Madurowicz, working also with Natasha Batala and Mark Marley from Ames, are very promising. We can do a good job reproducing the spectrum of the planet with a radius of 1 Jupiter radii, but still room for improvement. Again, I'm not going to talk about initial conditions. The last two things I want to talk about are occurrence rates for planets. So This is a plot showing the planets we found, their mass and semi-major axis. And the contours indicate our sensitivity. It's basically how many stars we could see a particular combination of mass and semi-major axis around, accounting for different random orientations of their orbits and different random chances of seeing a planet. You can see, although we only found a couple of low mass planets, out of the 600 stars we looked at, we could only have seen those around a few stars. And so that's a clue that the low mass planets, that the Jupiter-y planets are maybe quite common. However, this is the same figure split into high mass and low mass stars. All the planets we saw were around stars that were 50% or twice the size of the sun. None of the giant planets we saw were around sun-like stars. When we combine that with other techniques, it's possible that planets like Jupiter or above only occur around 25% of sun-like stars, and our solar system is maybe kind of lucky to have one. But to really answer that, we need more planets. And so the last thing I want to talk about is the upgrade to the Gemini Planet Imager 2. Again, I apologize for time. A lot of work has gone into understanding the performance of GPI, work co-led by Lisa Poinier at Livermore, Vanessa Bailey, who's now at JPL. We looked at 500, 600 stars. We took 25,000 images, and we have huge amounts of telemetry from the adaptive optic system and from external sources like, say, weather forecasting systems to try and understand, GPI is pretty good, but why can't we get sensitivity enough to see planets down here that are Jupiter mass, say, at 5 AU? One of the single biggest factors turns out to be wind and time. The atmosphere is always moving. The adaptive optic system is making its measurements, but it's always a millisecond late because it takes a while to make the measurements. The strongest predictor of our performance is basically how fast the atmosphere is moving. And at Cerro in Chile, let's see if I can get this movie to run. Be one of those movie worked in rehearsal, doesn't work in real life situations. Versus, all right. This one works at least. This is a movie of high altitude winds compared, and the little dot is where Cerro is. Basically, you can see that the jet stream aims right at the dam observatory. And so there's winds blowing over at 100 kilometers per hour, and my adaptive optic system is not keeping up with the turbulence as well as it should. And we have much more detailed modeling of this in a paper by my student Alex Medorowitz. GPI is also limited to fairly bright stars. The wavefront sensor we use to measure turbulence with the adaptive optic system needs a bright star. It's fairly complicated to use, and we've run out of stars in the southern hemisphere. And so the next thing for GPI is to move. We're going to take it and redeploy it from Gemini South in Chile to Gemini North in Hawaii. In the process, we're going to have to change our logo because you don't get Andean foxes in Hawaii, but you do get nenes. And we're going to rename it GPI 2 because we're also going to rebuild and upgrade it. It's going to come back to North America, and we're going to replace a lot of 10-year-old computer technology with modern computers, modern wavefront sensors, modern CCDs to increase our sensitivity. It's actually being led mostly by my former postdocs, Jeff Chilcote and Quinn Konopaki, and with a lot of support from the previous GPI team. We've been hoping to start the upgrade last year, but of course we couldn't even get the instrument out of Chile, so now it'll probably be deployed on Gemini North in about 2023. It's going to have an upgraded photon counting wavefront sensor using something called pyramid wavefront sensor technology, so we can go on much fainter stars. The real-time computer for the adaptive optic system will reduce the effective delay in correcting turbulence from almost 2 milliseconds to half a millisecond. So we'll do a much better job on bright stars, and will be designed to operate efficiently for a huge variety of survey projects. So to allow some time for questions and to respect everybody's time finishing at noon, some conclusions and some platitudes. Direct imaging with current technology doesn't get a lot of planets, but it does probe this unique piece of phase space, the outer parts of solar systems where wide orbit, high entropy, energetic, massive planets live. It's a way to test planet formation models and to test atmosphere models, which really are not yet good enough to let us learn everything we want to about the planets. There's a lot we don't know, like the initial entropy of the planets, which I could talk about a little, the clouds, the dust, and so on. In the near future, GPI 2 will expand our target sample. We'll be able to look at lower mass planets, really Jupiter analogs. We'll look at younger planets so we can see their evolutionary history. In the same time scale, the James Webb Space Telescope will let us study planets at longer wavelengths to finish those spectra that I showed and understand the complete spectral energy distribution. In the mid-future, we're going to have to move to space, and space-based instruments will start to be able to see mature analogs to Jupiter, things like the Nancy Grace Roman telescope. And in the far future, as I said, the same technology and techniques we've talked about here are going to be applied not to glowing red blobs, but to little blue blobs that will actually be analogs to Earth. So let me stop there to allow some time for a little bit of questions, and again, to thank you all for the chance to talk to you.
Thank you, Bruce, for the great talk. So yeah, if you have any questions, please enter them in the chat field, or you can, if you want to ask your question verbally, just like put a Q there or something so that I know to call. And otherwise, please meet yourselves and we can give Bruce Macintosh a nice round of applause.
See, just responding to the question Lauren asked, now that I can see the chat again, determining the ages of stars is pretty complicated. It's a mix of 2 or 3 things. So partially it's from stellar evolution models. As stars get older in this early history, they still contract, and so their brightness changes as a function of age. They haven't settled into their perfect equilibrium. They spin very rapidly when they initially form, and in turn that drives a strong magnetic field and a very active magnetosphere, which produces emission lines from hot stuff in their corona. We also look for groups of stars. The computer models aren't good enough to determine the age of every star, but if you can find a group of 8 or 9 stars where you trust the computer models for one of them, you can infer the age is the same for all the other stars. And so we have kind of a medium scale cottage industry of looking through the sky to find 30 million or 100 million year old stars using a variety of these techniques. But I would say we still argue a lot about the relative ages. Or another clue to youth, excuse me, is the presence of lithium in a star. Stars are really good at burning lithium. Lithium fuses really easily. And so if you find a star that still has a little bit of lithium left, you know it's young.
There's a question from Doug Driver saying, how unlikely is it that any random stellar planetary system offer planet and transits for observation?
It's pretty unlikely. You have to line the planet and the star up exactly on top of each other. For a planet, for a solar system, like our own, it's sort of chance in 100 to chance in 1,000. So if you want to find these, you have to look at thousands and thousands of stars to find the ones that are lined up. The good news is with modern large format cameras and digital data and computing, you can do that. And so NASA has launched missions like Kepler and TESS that looked at 100,000 stars each to find that handful that are aligned pointing towards us. You can also imagine that's biased. Your chance of getting that lineup is much stronger if the planet's closer to the star. Also, no one believes you unless you see it pass in front of the star 3 times. For Earth, that would take 2 or 3 years. Kepler mission failed its primary mission after 3 years, and so it barely had enough duration to have a chance of catching an Earth-like planet, let alone a Jupiter, which would take 12 years to get even 2 transits. So you have to get lucky, or you have to have huge computers and big cameras, and fortunately, we have huge computers and big cameras now.
So I have a question. So once you account for all the biasing effects, like you see a lot more planets very close to their stars, is our solar system atypical, or is there still not enough data to try to tease out like what the distribution of the mass radius distribution is for solar system planets?
It's mostly that right now we don't know. So the Kepler mission, that best transit mission, discovered about 2,000 planets. If every star in the sky had a solar system just like our own, Kepler would have discovered 2 planets instead, because of that chance alignment, because of details about how noisy the stars are and things like that. And so we're still essentially blind to solar systems like our own. We're just starting to discover Jupiter analogs with imaging and with Doppler shifts. We can see from this diagram that the other solar systems are very different than our own. Whether that means that we represent an outlier, that most systems just have mini Neptunes and hot Jupiters, and you've got a small chance you don't, or whether it's kind of bimodal, that there's one process that formed these solar systems and one process that formed our other solar systems. Honestly, I think the evidence is currently unclear. You know, our solar system is so different. Why is that? And I don't think we really know right now. I tend to think we're weird, but not everybody else.
There's a question. Paul Porter saying you showed 4 planets circling a star from a perspective perpendicular to the plane of the solar system. How do you deal with tilted systems? Does it complicate analysis of planet radii?
Yeah, I mean, this system, let me start my video again because I love it. It's almost perpendicular to our line of sight. It's actually probably tilted by about 30 degrees. We've watched the orbits closely enough and measured them precisely enough that we can try to recover the tilt of the whole orbital system, but it's close to face on. When you're seeing planets from thermal emission, it doesn't matter too much what direction you're looking at them from. You'd get the same thermal emission from, let me find big glowy Jupiter again. You'd get sort of the same thermal emission from big glowy Jupiter if you're looking at the poles, although not exactly. And so if the planet is broken up into partial clouds, then you do have to worry a little bit about orientation. If we were seeing light reflected by a planet, if we were seeing a mature Jupiter and the light it scatters, then you really would have to worry a lot about the phase function, about the reflection in different angles. And so you'd measure the orbit, you'd try to estimate how tilted it is, and you'd use radiative transfer modeling to see whether you scatter more light in different directions. It's a good question. So I don't think it messes up the radii for the planets we're looking at now, although, you know, as I stare at Jupiter here, it does look like the poles are different than the equator. That might account for some of the uncertainty in brightness, but it'll become more of an issue with other systems.
Are you able to get Doppler velocity measurements for those systems?
Frustratingly, on this system, we can't. So there's an almost perfect anti-selection effect between us and the Doppler people, because we like young stars, like I mentioned. And you know, I said young stars are spinning really rapidly. They have strong magnetic fields. They have messy coronas. It means they're covered with sunspots. Sunspots are really bad for precision Doppler measurements. The planet will, you'll get spurious Doppler shifts as sunspots come and go, as the things of solar flares and so on. So all of our stars are, you know, one way we could find young stars is we could go to the trash cans of the Doppler people and find the stars they threw out because they were such a mess. And so right now it's almost unmeasurable. There's one system where with 10 years of telescope time, they have a tentative Doppler shift measurement that gives a mass, Beta Pictoris, which I only showed very briefly. 8799, we don't have a Doppler measurement for at all, in spite of a fair amount of trying. Very frustrating. There's a space mission called Gaia that looks not for Doppler shifts, but for wobbles in the plane of the sky, and that might be able to get us masses for some of these soon, which would be really cool.
There have been relatively recently, like about a year ago, there were images that came out of Sagittarius A or massive black holes. Is there a place for using the type of machine learning techniques they did to get like resolution images in imaging these planets?
So they did that in addition to fancy machine learning. They also, you know, as you know, the diffraction limit of a telescope is lambda over the wavelength of light over the diameter of the telescope. They had a telescope that was about 10,000 miles across because they used telescopes across the whole Earth and connected them together. You can do that at radio wavelengths, but you can't do it at optical wavelengths or infrared wavelengths easily. And even if you could, that still wouldn't be enough. So the two ways you could maybe get real resolution and show a picture like this or see continents that people have proposed. One is if you had a telescope that was not 10,000 kilometers across, but 10 million. If you had a network of telescopes formation flying through the solar system and you used interferometry techniques to synthesize them into a single telescope. That's pretty hard, but doesn't break the laws of physics. The other cool one that people have suggested is another way to get a lens that's millions of or hundreds of thousands of kilometers across is to use the whole sun as a lens. The sun's gravitational lens focuses light, And if you put a telescope where the sun, or an eyepiece or a camera where the sun focuses light, you can get angular resolutions that would let you see continents on Earth-like planets. The problem is that focal plane for the sun is 700 astronomical units out, so about 20 times the sun-Pluto distance, and we've only barely got spacecraft to Pluto, so you better get started now if you're going to get a telescope there. But again, laws of physics don't prohibit doing it that way. But yeah, the short answer is you need one way or another. You need a lens or telescope diameter of 1 million kilometers, which means you can't do it on Earth, but could do it elsewhere in the solar system.
Machine learning, that's what they use.
And the machine learning was really just part of the, this thing you're thinking of is the sort of donut picture that's the image of the black hole accretion disk, right?
Mm-hmm.
Yeah. So machine learning was just kind of an icing on the cake part of it. The core was that they had information to begin with, that they were, they had 2 or 3 resolution elements across the disk, and then you use machine learning to boost that to 6 or 8 or 10. But you got to start with 2 or 3. And right now, with our telescopes, we have 0.000001 resolution elements across the disk of the planet. And so machine learning might increase that to 0.00002 pixels across the planet, still not enough. So once we get a little bit of resolution, fancy machine learning can boost it, but you got to get a little bit of resolution first. Super resolution gives you factors of 2. We need a factor of 1,000. Good question.
Right.
You could use, actually, just to answer it, to be somewhat more about that, you could use the rotation of the planet as bright spots come and go, and people did that for Pluto to get hints of Pluto's structure. So that's a possibility.
Any other? Right. Well, thank you, Bruce, for thank our speaker again. Hope
Thank you all.
see everybody
Lovely
here
to
next time.